So today I'm going to tell you about some work we have been doing on how to verify control systems where the controller would be something trained using modern machine learning algorithms and implemented as neural networks. So the context for this work is verification of software. And so just to give you context of where verification plays a role. So this is how programmers design software. So a programmer may start with some specification in mind and generates a program, and in the end the compiler translates it to executable code. And once this programming or design phase is over, the testing and validation people come into play. And so they sometimes query the programmer to give some specifications. Sometimes they write their own test cases and use analysis tools to check either the source code or the binaries to find bugs in the program. And once these bugs are found, they're reported back to the programmer, and then the programmer may go and fix these. Right? So in any organization, this role between how the programmers who design the programs and the verification and validation engineers who test and verify the programs, they are usually separate organizations. And over the years, where the formal verification technology has contributed is in developing these analysis tools, introducing more and more automation, letting programmers, letting the testing and validation engineers check these the conformance of the code or either the executable code or the high-level models with respect to formal specifications in more powerful ways, right? And some of the techniques that have been developed dating back to, say, early 90s are things like model checking, static analysis. More recently, there has been a lot of progress in developing proof assistance. And we are getting closer and closer to this dream where we would have fully verified systems. So this technology has matured a lot to the extent where the lots of companies now have they invest heavily into verification tools. It actually started with Intel. So in the early 90s, there was this FDiv bug in Intel's processors. As a result, Intel said, well, this actually costs a lot of money to find bugs late in the design, and so they invested a lot in formal verification technology, and symbolic model checking played a key role in that. And then in the late 90s, Microsoft realized that lots of bugs, lots of crashes that are caused in their operating systems are because of bugs in third-party device driver code. So they invested in this technology for software model checking, and this tool called static device verifier is now used widely within Microsoft to make sure that the device driver code that's written by third parties is actually conformant to a variety of specifications that Microsoft releases. And more recently, Amazon has actually is investing a lot in making sure that the security policies that they advertise to their customers are in fact enforced, and that would and that can be actually an industrial advantage in selling their cloud services. So this is actually an exciting time for research in formal verification due to this widespread industrial adaptation. And the companies that are more relevant to what I'm going to tell you about today is actually MathWorks. So MathWorks is they build these design tools for design of control systems. So say a software in a car or a software in a medical device, and so typically that type of control software is designed using MathWorks products like Stateflow Simulink and MATLAB. And now MathWorks has a heavy investment in integrating formal specifications and analysis tools within those design tools. So, given that some of the academic research that happened in the 90s and early 2000s is slowly shifting into industrial practice. Now we have to think about what are the new challenges for academic researchers. And the one that I'm going to tell you about today is that the software now includes components that are trained using machine learning. So of course, I have a couple of slides on machine learning, but I don't have to tell you that that's like the exciting development in computer science, and that's what's enabling lots of these new applications, right? And that, as I'll tell you, that raises new challenges regarding how we verify systems. So in particular, I'm going to talk about neural networks. And in recent years, there has been a lot of excitement about the potential of neural networks in applications where we don't know how to write traditional code. And a particular example is perception or natural language processing, and there have been lots of successes. And as a result of that, there is this temptation to use them in control applications. And by control application, I mean deciding, how fast to go and in which direction to steer the car. Now, of course, you must have heard a lot about autonomous driving. But if you look at what actually happens in an autonomous car, there are lots and lots of components. And for the high-level tasks such as perception, figuring out where the obstacles are, or is there a pedestrian in your way. So for that, machine learning is the current technology seems pretty reasonable. But I'm going to talk about more lower-level control, where you are actually deciding how fast to go, and that's where actually the technology is not mature. And the main reason is that we don't have good safety guarantees about that, right? So what's a control system? So this is, if you open any textbook on control, this is kind of the first diagram that you see, where a controller is making some measurements from the plant using some sensors. So think of a car as the plant. So this is the traditional standard terminology from control. And the controller is the one that's deciding how much pressure to apply to the accelerator, right? And then, so that would be the control input, and that then is fed to the plant. And this is called a closed loop control system, where the controller is making some measurements and then making autonomous decisions on what to, how to impact the plant, right? Yeah. So there are no humans involved in this closed loop system. And the question now that we want to ask is that if for such a controller, is it correct with respect to some high-level requirements? And so in the context of autonomous driving, think about avoiding collisions, right? So that's like a basic safety requirement. And if we cannot assure that, then of course nobody would be using autonomous cars, right? So, but we know, and you must have seen these kinds of examples in the last few years, that the neural networks are that they have been demonstrated not to be robust, right? So, and this is a famous example where you have some image. Okay, I'm not sure if this is working, but yeah, it's okay. I don't need the pointer. So yeah, so on the left you see an image which is classified as a panda with with 58% confidence, and with some very carefully crafted noise. You just add some noise to that image, and the image on the right, which all humans would think is pretty much the same as the left image and would classify it as a panda, but that gets classified as a gibbon with very high confidence, right? And so the reason, of course, is that because the way these neural networks work, we don't have a great understanding in terms of how exactly what's going on, and how these parameters can be tuned during training in some mysterious ways, and then on the test data they may the whole classification could fail quite miserably. So this is not a big problem if you are using a neural network to do some natural language translation, and once in a while the Siri interprets what you are saying completely differently, and you can live with that type of an error, right? But if you are using this to drive a car, then this could be a big problem. And in fact, there have been I don't know what happened. Okay. Yeah, so so in the context of driving, again, people have designed these attacks. So the one on the left gets classified as a stop sign, but if you put some patches on that stop sign and the lighting is different, and then it gets classified as a speed limit sign, right? And this is clearly a problem, right? So this has spurred a lot of research in machine learning community to design training algorithms that are robust. And what they mean by robust is that if for a given input, if there is a specific classification, and if you perturb the input slightly, then that, ideally we would want the classification not to change, right? And that's called robustness for neural networks. But that's not good enough for closed loop control systems where, in fact, it's evolving over time, and at every time step you are getting some classification, and that's going to affect the decision that the controller makes, and that's going to affect how the plant evolves. And what you're really interested is not in the robustness of a classification at one step, from this input to output function, rather a temporal evolution of the entire system and making sure that there are no collisions. And I think that's where formal verification technology can help. So formal verification, as I mentioned earlier, there are lots and lots of tools for formal verification. The one that I'm going to talk about is called model checking, which is a more automated method for doing verification. And the model checker takes, in this context, would take 3 inputs. So one is the controller. So this controller in the current context would be implemented as a neural network. The plant would be a model of the car, and typically these models are designed using tools developed by a company like MathWorks. So this is actually a simulating diagrams where you can model the car. So before you actually generate code, you would at least want to do some kind of simulation, even if not for complete formal verification. So modeling is very common in control design. So you would first build a model of how the car would respond to the signals that the controller is giving. And then for the purpose of formal verification, you need a formally specified logical requirement. So in formal verification, the most commonly used framework is some version of temporal logic. For the purpose of this talk, I'm just looking at safety requirements, where you could say that I want the system to stay within certain set of safe states. So again, think about avoiding collision. So you want to be, let's say, away from all from the walls. And then what the model checker is required to do is to analyze this controller in the context of this environment and make sure that the logical requirement is valid on all possible executions of the system, right? And the difference between more traditional simulation is that in simulation you pick maybe a specific initial condition and look at a specific execution, whereas in formal verification and in model checking, you are trying to analyze all possible executions. So for example, if a sensor has a noise, then you want to see what happens for all, in the worst case, for all possible values for the noise, how the reading is changed as a result of that, right? And if not, then if the system is not safe, then the model checker would give you a counterexample, and that can be used as a feedback to the designer, right? So instead of telling you a lot about the underlying techniques, I'm actually going to illustrate the way we analyze the system using a specific case study. So my talk is going to be going to follow this outline, where I'll tell you about a platform called F110 Autonomous Racing Cor. So this is a nice platform that's becoming very popular in the context of student projects and so on. I'll tell you about that. It's a miniature version of the car where you can try out your algorithms for how to do autonomous driving. Then I'll tell you why one would want to use a neural network-based controller in this context and how you design such a controller. And that will lead us to how, what's the verification problem. The way our current tool solves this verification problem is by reducing it to verifying hybrid systems. So that's a specific area of research within formal verification. And I'll tell you about hybrid systems verification a bit. And then the tool Verisig that we have built. So there is a website for Verisig where a lot of this information is available. And this research is joint with a number of faculty at Penn, in Supply, George Pappas and Jim Weimer, and Radoslav Ivanov, who is a postdoctoral researcher, and he's actually the one who did most of this work. So what's this F110 autonomous racing car? So this is this is a picture of this platform. It costs about $300-400, and it's now becoming very popular. There is this website f110.org, and there's a lot of information about this there. You can order it. There is an annual competition which is held at Embedded Systems Week and Cyber Physical Systems Week, where students from various universities participate in this competition. And the competition is actually to program this car to go as fast as possible. So this racing aspect makes it quite exciting. So, and if you look at the basic components that are needed to to program this car is so there are things like perception, control, and things so the basic elements of design of controllers to build autonomous cars. And this platform was built by Rahul Mangaram, who is a professor in electrical engineering at Penn, and his former student Madhur Bail, who is now a professor at University of Virginia. So I'll actually show you what this car does. This is kind of a video. So this is not a complex problem in autonomous driving, but it still has lots of elements. So here it's racing through these corridors, and in the competition, the track or the corridors are not known in advance. So the car has to figure out the car has to figure out where the walls are, and it's a racing competition. So you have to complete the lap as fast. Whoever completes it first is the winner. And of course, if you collide, then you are dead, right? So it's just like a racing competition, like as in F1 racing competition, right? Yeah. So what's the design challenge here? So you have to implement this controller has to be real time, right? So it's getting the sensory inputs, and they're using this LiDAR. So LiDAR is this new technology where you send these arrays in different directions, and you get a measurement of the where the nearest obstacle is, right? And based on that, you have to then decide whether you should be speeding up or should you turn and things of that. And then you have to translate it to lower level control signals, and in particular in this case it would be the steering and the speed. So as a control design problem, then we have to think about. So let's try to get down into the actual control design. So the state variables here are the position. So this is you can think of it as the position of the car as a point in 2 dimensions. So x1, x2, the linear velocity, the angular velocity, and the orientation. Right. So there are lots of standard models for how this type of a car would respond to the throttle and steering. So a well-studied model, it's called the standard bicycle model, And I don't want to get into the details, but on the right-hand side, you see some differential equations. And so this would be kind of textbook models of how the car responds to the control inputs. So in the specific case, there are two control inputs, the throttle UT, which is to change the speed, and the steering to change the direction. Right? So what we really want to do is if you think about, okay, what's the code that you have to write? So you have to determine the throttle input and the steering input as a function of the current state. So this was like a 5-dimensional system. So you have five variables, and then it's of course the basic thing that you don't know is where the walls are, right, and where the obstacles are. And in this specific platform, it's as I mentioned, it's using these lidars, and you get this array of vectors. And so again, the details are not super relevant for the talk, but just for your information, this in the specific platform, basically you get this lidar rays span from minus 135 degrees to 135 degrees. So basically you are getting this span, and you get about 4 readings per degree, and in each direction you basically send this ray, and you get, okay, the value 5 would mean that, okay, well, the first obstacle that this ray in that direction hits is at 5 meters, right? And if you don't see anything up to 10 meters, then the value would be 10, right? So so now there are lots of companies which are trying to improve this LiDAR technology, and it's likely to be the dominant technology for doing low-cost technology to figuring out to map the surroundings, right? So the cameras are more expensive. Also, they're computationally problematic if you want to make decisions in real time, whereas these LiDAR readings, it's a cheaper way, and you can just send the things in different directions and get the readings. Yeah. This the car. You can reduce the speed. Yeah. Yeah. So this is actually, this is more like a toy experimental platform where you are just like racing, right? Yeah. And on the actual car there are brakes, but they are not. I'm not modeling them for in this specific context. But in the end, well, at the end of this run, you have to stop, right? So yeah, there are brakes. Yeah. Oh, I mean, the actual. So this is more like an idealized version of the real autonomous driving problem, right? Yeah. But the good thing is that there is this actual platform, and you can try out different control algorithms and see how well they work. And there is a kind of exploding interest in this specific platform because it's quite cheap. It's very hard to do experiments in real autonomous driving. I mean, you need to basically convince Toyota to give you a car, and yeah, that's very different ballgame than just ordering a $400 kit from a website and trying out different strategies on this platform. Right. So okay. So this is. So we are going to focus on on design of this specific controller. The requirements here are clear. Avoid collisions. You have to follow the racing path. And actually, there is also this nice quantitative requirement that you want to minimize the finish time. Right? Yeah. But I'm going to focus on safety in this talk, which is avoid collisions. Right? So when you want to apply formal verification, many times that can be a bottleneck. What's the correctness requirement? Well, in this specific context, at least this basic requirement is very clear, and it's clearly tied to what you want the system to do. Okay, so Okay, so how do people, okay, so if you gave this problem to a control engineer, well, they would, you know, they would use things like model predictive control and so on. So there is, we do have understanding of how the car would respond to the changing of speed and steering, and then you could predict what the car would do, and then make sure that you know, there are no collisions, right? Yeah. But I'm going to focus on using neural networks to do this problem, right? Most people, in fact, you know, I would say everyone who enters this competition would have just analyzed the problem. It's not super complex, so you can think about, you know, what would be a reasonable strategy, right? And it's your guess would be as good as mine, you know. So if we are heading in this direction, and if I'm sure that there's no obstacles within, let's say, some theta degrees in both directions, I could just keep going in that direction and maybe even speed up, right? Yeah. And then if I see an obstacle, then you have to think, okay, well, should I be turning left or right, and by how much? And you can try to write code. But even as you start thinking about it, you would realize, well, you know, you have to do some kind of analysis, and it would be heuristic, and things can start getting complicated. And if you think, okay, you know, but how much space do I need, and you know, what's the tolerance that I need? There are lots of parameters, and the way you would try to then actually write code is by trying out different values of these parameters, and then adjusting them, and you know, trying maybe put it in some simulation environment, see how well it works, and then keep doing this process till you are convinced that the specific algorithm that you have is reasonable. And what learning would do, if you are trying to use some state-of-the-art algorithm based on reinforcement learning, it would just be automating this process, right? And so in the learning-based approach, you can think about what you want to learn is this function, which well, the ut and uh were the steering and the speed, and then it's a function of the current state and then the vector of this LiDAR readings, right? And if you were to, so that's, you know, that's, so learning would be a good thing in this context, where without trying to analyze exactly, you know, what the control strategy is, you could just initialize this function and then just adjust the parameters, and hopefully it will converge to the right function that you want. And a good, the benefits of this approach is that you don't need the model, because in the traditional control design, even though since this is a car whose dynamics we understand reasonably well, you would have to analyze how the car is responding. Whereas here, what you could do is you start with this function, put it in a simulation environment. And in fact, there are lots of gaming environments which are quite suitable to see how a racing car evolves in, you know, in this, in your video game, right? And those would be, so you don't have to then start and do any prediction in terms of how the car is responding to this control signal, right? And another reason why this using neural networks in this context is could be useful is that the evaluation of this function then would be fast, because in traditional model predictive control, implementing it in real time can be a challenge, because you are doing some computationally expensive task to figure out, you know, what the speed and the direction should be. As a cons, well, you need training data. But in this specific context, there are lots of simulation environments available, so you could try implementing different strategies there. But the one that we want to focus on is that, okay, how do you get safety? So if you do it using model predictive control, you have good guarantees about that the car would be stable, you know, you would be avoiding collisions. And here, we don't have those kinds of guarantees if I just train it using some simulation data and implement it as a neural network controller. But this also is good case study for designing verification techniques for systems where the controller is implemented as a neural network, because that's a scientific challenge that I mean, forget the specific case study, right? But if I give you a controller implemented as a neural network, how would you verify it, right? So what's a neural network? So most of you must be familiar with it, but just one slide summary. So here is a neural network where on the left you see the inputs, and so just a way of implementing a function from a continuous function from inputs to outputs, and then you have a number of hidden layers. This is fully connected feed-forward neural network, and then you have some outputs, and the at each node it's basically some nonlinear function of all the inputs. A popular nonlinear function that each neuron implements is this rectified linear unit called ReLU, which is basically it's a max of 0, and so W are the weights, and input is the vector of all the outputs of the previous layer feeding into this specific input, right? And then during training, what happens is the values for this weights on these different edges, that those get adjusted so that the output is the desired output as a function of the inputs, right? So now this is how then the neural network-based controller for F110 car would look like. So you have the controller which takes the measurements of the LiDAR. It turns out that in fact the state is not even needed in the specific neural network that we trained for this car. The neural network just looks at the measurements coming from the LiDAR and decides what the current speed and the direction should be, and those control signals then are fed to the car, and then that determines the state. And of course the LiDAR measurements depend on what the environment is, what the geometry of the corridors and the racing track is, and where the car is, right? Yeah. So this would become then our closed loop system that needs to be analyzed. So how do we train a neural network here? So it's more of because of the limitation of current verification techniques that we have, we keep the speed fixed, right? So just for the purpose of this experiment, so all that we are changing is this steering, which is this UH, and all we are checking is that, okay, well, if we put the car in a corridor that's turning left or turning right, will it turn correctly without hitting the obstacle, right? Yeah. And so this heading direction is then, and it's a function of the LiDAR measurements it's getting, and then the weights of the neural network, and the weights are the ones that are changed during the training phase. And so the way to train this is then you fix the hallway geometry and use simulation for different initial conditions. You generate a trajectory using simulation. Design a reward function. So in this case, the reward function would depend on how long it takes for the car to crash, and of course, the longer that time is, the better the current values for these weights are. And so in actual car, there are all these other criteria that it's not only that you should avoid collisions, but the car should be stable, or the ride should be smooth. But again, there are known ways to handle that. You basically penalize for if you're changing the control signals too fast, you want to add some penalty. So designing this reward functions is also kind of it's a magic art, and one has to play with different reward functions. That's another opportunity for research, how to design good reward functions for training of neural networks in general. But in the end, we get a neural network with 21 inputs. So actually, in this platform, there are 1,080 readings. So this LiDAR readings you get, it's an array of 1,080 measurements. Our current verification tool is not, it needs to scale up better. But we basically sample only 21, so we use only 21 readings. But the good news is that the neural network that we have trained is deployed on the actual car. In fact, the video that I showed you was the one that was implementing this neural network-based controller. So it's actually, and it didn't collide, so that's good news. As a neural network, and this is not, it's pretty, the machine learning people would say this is kind of tiny. It has 64 neurons with, the activation function is actually sigmoidal. It's not ReLU, so this is sigmoidal is probably the second most common form of activation function. And later when I tell you about the analysis technique, I'll tell you why these sigmoidals are interesting. And it has only one output because we have kept the speed fixed, right? Okay. So, so at this point, again, I want to revisit this question that should we be interested in verifying these systems at all, or what can formal verification add to this area, right? So safe AI is actually, it's a broad area, and if you look at it's viewed as a national priority in pretty much every country. How do we make sure that the modern AI systems are trustworthy, safe, and so on? And there are lots of researchers in machine learning who are thinking about this problem, that can we make decision making fair, can we make decision making robust, safe, right? And of course the first response is and should be that you want to design better algorithms, right? And that's we don't want to dispute that. But integrating symbolic or logical reasoning in training of neural networks or in reinforcement learning, so like this whole area of safe reinforcement learning, it's a challenging area, and the progress is being made. But we concurrently and independently, we want these techniques to analyze what has been trained, right? And again, going back to this picture that I showed you at the very beginning, which was that in every organization, people who design and build systems are separate from people who do testing and validation. And the hypothesis is that even in the future, even though the design and implementation is being done using modern machine learning algorithms, and these algorithms will evolve and would be more trustworthy as time goes on, there will still be this group of verification engineers who would take whatever has been designed, trained using the state-of-the-art algorithms that would be there, let's say 20 years down the road, and would try to independently come up with tests and specifications and make sure that the system that has been given to them it conforms to the specifications, right? So so that motivates actually trying to look at the current verification techniques and see how they can be improved and adapted to this case where the controller or the components have been trained using learning algorithms. So that's with that motivation. What's the what can we do in this specific case? Well, so this the training of this neural network actually stops once it has converged on the given training data, and but at that point you don't really have any logical relationship between inputs and outputs. Then when it's handed off to us, we could say that okay, we could try different geometries than the ones that were used using training. We can also build models of errors in the LiDAR readings and then try to make sure that even when these LiDAR readings fail, even when there is noise, under all those conditions and for a range of initial conditions, the car avoids the collisions, right? So that would be our verification problem. So going back to this idea of then model checking, so we have now this controller, we have a model of this plant, and so it turns out that this is what we call hybrid dynamical systems, and I'll tell you about that in more in a minute. And the logical requirement is this set of safe states, and you want to do a symbolic simulation, analyze all possible executions of the system for a range of initial conditions and the range of noise parameters, and make sure that any execution that's generated for this is safe. So this area where you analyze models where the plant is described using differential equations, so that's called hybrid system. And it's a combination of state machines and dynamical systems. So here is a simple system with two modes on and off, and to this you add differential equation. So in this case it's a single differential equation, and so when this is kind of a thermostat which says that when it's on, the temperature x changes linearly according to the differential equation. Dx by dt is equal to some constant times x, and it's a closed loop system. So when the temperature is greater than 68, it switches to this mode off, and when it's in mode off, the temperature decreases according to the differential equation, dx by dt equal to minus k prime x, and then when x is less than 63, it can switch back, right? So these are what are called hybrid automata. This is something that we had defined in early 90s, and over the last 25 years there has been a lot of progress in studying these hybrid dynamical systems, and this has been across interdisciplinary research between computer scientists and control theorists, and we have brought ideas like logical specifications, how the concurrency, formal verification, in conjunction with ideas from control theory like optimal control, stability. So analyzing stability of a single dynamical system when it's in a single mode, that's well understood. But when you have this switching between different dynamical systems, things start getting more hairy, and the mathematical results that are available are a lot weaker. And so this is basically an interaction between discrete software and continuously evolving environment, right? And people have found applications in automotive controllers, coordination protocols, robotics, medical devices. Actually, this is where there's been lots of interest in modeling, say, the heart and then the pacemaker that's monitoring the heart and making control decisions, and then trying to verify the closed loop system. Also in systems biology, and the companies like Toyota and MathWorks, they have that's some of the places where some of this technology has been transferred, right? And so we want to build, so I don't want to give you a tutorial on hybrid systems because I want to focus on how do we analyze neural networks, but that's kind of the context. And I'm going to, so let's take it for granted that if I have models which look like some integration of state machines and dynamical systems, we have some existing technology to analyze some safety properties of such a system, right? So now going back to this neural network based controller, so the specific computational problem is that I'm given a neural network for the controller. The plant, or in this context, this F110, say, racing car, is modeled as this hybrid system, and we have a predicate over the states of the plant and the environment. And in particular, in this case, I want to make sure that there is no collision, and we want to prove that this neural network in conjunction with the plant satisfies this fine, right? So the specific challenge from a verification perspective is that this neural network is a complex nonlinear function, right? And so now it's been trained, it's given to me, and I just want to make sure that it satisfies at least this basic property of avoiding collisions, right? So this is one potential. So this is very new. So lot people are trying out different ideas on how to tackle this problem. Here is one strategy that I just want to mention, though I won't focus on it, is use some ideas in abstraction to get a simpler representation of this n, right? So for example, you could say that actually even for training, maybe a neural network is useful, but in the end, maybe it's a simple decision tree. And can I extract a decision tree which approximates the given neural network, and I can then use this decision tree, which is hopefully simpler, and then replace basically this neural network n by that decision tree, and then show that the decision tree in conjunction with the hybrid systems model of the plant satisfies the safety specification. Right? And during the break I can tell you more about this, but here is an example work on this, which is called programmatically interpretable reinforcement learning, and there is a paper in ICML. Actually, if you look at this past NeurIPS, there are again 3-4 papers on this topic. So basically using some ideas in program synthesis to synthesize decision trees from neural networks. Right? Here is a potentially interesting alternative strategy, which I would like to explore, but we haven't done it yet. So this is that you could say that what I really want to prove is that this composition of n and h satisfies certain property. So an age-old idea in formal verification, forget formal, even people started building systems, the basic idea would be modularity, right? So what's the property that n should satisfy, right? Yeah, given this context h, right? So if I can articulate this interface specification or the assumption about the neural network that I need to prove the property phi, if I can find that, then I could say that, then I have to separate problems. I could say that the neural network should satisfy this input to output specification, and then that input output specification in conjunction with h satisfies phi. But this is easy to say, but in this specific context, it's not clear what this specification, input to output specification of the neural network should be, because that's likely to be very stateful and complex, but it's an intriguing thought, right? And but there is, if one could do that, then we can use this tool, which is actually it's a very nice tool developed at Stanford. It's called ReluPlex, which is designing a specialized constraint solver to prove input-output properties of neural networks. So if you think about, say, these ReLUs, it's basically it's a linear function with some little bit of non-linearity, right? Now you can so those of you who are familiar with constraint solvers, the one that have made a lot of progress recently, they are called SMT solvers, and so they are basically constraint solvers where lots of heuristics have been engineered so that they can scale up to very large problems, right? So we started with propositional constraints, and later there was combination of linear constraints and propositional constraints, so like a linear integer arithmetic. And now we can go one step further and say, okay, well, now I have these ReLU constraints where I don't want to actually expand them into separate this Boolean and linear constraints, but I want to design specialized constraint solvers for that. So that's what this ReluPlex does. And there is lots and lots of research in the last couple of years on designing specialized constraint solvers. But to use that, you would need this separation between the neural network and the model of the plant, right? So if you had this nice interface specification for what the input-output relation should be, you could use this ReluPlex. What I'm going to tell you in the next half an hour is what we have been trying, which is trying to prove safety by computing the set of reachable states of this closed loop system using tools that were originally designed to compute the set of reachable states of hybrid systems. And the basic idea here is that since we already have the to analyze the car, we do need to analyze how like symbolic simulation techniques for differential equations can be built on that technology. And for that, what you have to do is then try to reduce this neural network to something which looks like differential equation. And here are like a couple of papers, one that appeared in this hybrid systems conference last year, and the one that's about to appear next year. There are other efforts also along this lines, right? So before I tell you the connection between this sigmoidal neural networks and hybrid systems, let me give you one slide summary of how the reachability computation for hybrid systems looks like. So in any verification tool. The core problem is to symbolically compute the set of reachable states, and this is depicted visually here. So in simulation, you're given a specific initial state, and given a model of the system, you compute the execution. But now imagine, instead of a specific initial state, you are given a set of initial states, right? And you want to design a symbolic simulation algorithm where you say that what would, if the initial state is in this set, where would it be after one step, where would it be after two steps, and so on, right? And you keep doing that, and you have some specification of what's safe and what's unsafe. At any point, if the current set intersects with the unsafe states, you have found a counterexample. And then to actually implement this algorithm, this is a very simple algorithm, but to make it work, you have to then think about, okay, how is the system represented? What are the types of the variables that describe the state of the system? What would be a good data structure to represent the set of states, right? And for example, if all the states are Booleans, then the set of states can be represented using, say, ordered binary decision diagrams. If in the case of hybrid systems, things start getting more complex. And the basic problem is that the first guess would be, let's try to use some kind of polyhedra to represent sets, because we know how to manipulate polyhedra. Of course, in higher dimension, there is a scalability problem, but conceptually, polyhedra seems like a good representation for representing initial states for continuous time systems. But even for simple dynamics, if it's, say, the dynamics is given by a linear differential equation, like x dot is equal to ax, then if the initial set of states is like some rectangle, it may evolve in some more complex ways, right? And so then you can't really compute the exact representation of the set of reachable states, but what we actually do is approximate it by union of polyhedra. And so that's the basic idea. Now, how to actually do it, how to make it scale, what's the right representation. There's again lots of ideas and tools that have been developed, but this general idea is called flow pipes. So, so here is if I start in that x0, as time evolves, it's some kind of complex thing, but I could splice up the time into lots of small intervals, and then do some optimization integrated in numerical simulation to get an over approximation of where the system would be within that box. Right? And so FlowStar is an example tool which implements many of these ideas very nicely. It's kind of a state-of-the-art tool, and it's been used in a number of medical applications. Yeah? Yeah, that's a very good question. So in fact, we don't know how to do that. So actually, if you think about the application of neural networks, let's say in image classification, this would not be the right technique. I mean, maybe people would come up with cleverer ways. But let's go back to this F110 racing car example, right? There, I'm not interested in what's happening internally. I'm just interested in system level properties, and what are the initial states of the system. I could say, the car is maybe, I could say specify bounds on where it is with respect to the edges of the corridor, and bounds on which way it's heading initially, right? So so those would be, so the state there is really the position and the direction of the steering, and I could imagine some interval bounds on those. Yeah, right, yeah. But so for robustness, in fact, the specification is not clear. Whereas for this closed loop system, in the context of, let's say, autonomous driving and so on, the set of initial conditions is clear, the specification is also clear, right? Yeah. And in fact, for that problem, I wouldn't even know that, robustness doesn't really capture what you want to do. What's the specification? Well, if the image contains the dog, it should be classified as the dog. But that's really the specification. It's not clear how you formalize it. Whereas here, if I say that here is my hallway geometry, and here is the position of the car, and then I have a clear state space, and I could say, oh, these states are unsafe, and these are safe, very clear. Unsafe would be something where the distance between the car position and the edge of the hallway is less than some epsilon. Okay, so let's so far it was mostly like background and motivation. I have a few slides which get into a little bit of technical detail into how we actually analyze this neural network using hybrid systems technology. And the one, actually we have now a way of handling ReLUs also, but the initial one that we tried was, because the match was really good, was the sigmoidal activation function. So what's a sigmoidal activation function, if you haven't seen it? So this is another kind of activation function for a neuron. So I'm illustrating it in a single dimension, but there is an analog in higher dimensions. So x is the input, and sigma of, this is the function, sigma of x is 1 over 1 plus e to the power minus x, right? So that's what this function computes, and well, I mean, if you look at this graph, it's clear what that is, right? And so it's basically, so you can think of the ReLU as kind of a discretized version of this. Here the nice thing is it's continuous, right? And so for most of the time it's 0, for most of the time it's 1, and in between it has like this exponential ramp up, right here. So of course, if I give you a specific value of x, computing the corresponding sigma of x is that's what we would call simulation, right? What's the symbolic simulation problem? If I gave you a range of x, and actually in one dimension maybe it would look a bit simpler, but imagine the generalization of this in multiple dimensions. So I give you an interval set I, and I ask you to compute the image of that set under this transformation sigma, right? And you want as good an approximation of this as possible, right? So one could go off and try to design specialized algorithms to do this, to build good symbolic computation techniques for that, right? But we said that, well, let's, as a first shot, let's try to build on this hybrid systems technology, because here these conceptually, this is very close to computing the set of states of a dynamical system. Right? I mean, if you think of so instead of x, let's think of this, the horizontal dimension as time. So this is what a typical continuous evolution looks like, and that's what we have been doing in computing rich sets of hybrid systems. But how do we make this connection precise? So the main observation is that if I look at this function and if I look at the derivative of this function, then it satisfies this equation that the derivative of sigma is actually sigma times 1 minus sigma. Right? So it's kind of a linear difference. There is a nonlinearity, but it's what we would call, well, it's not super complex. It's a bit nonlinear, but not too bad. Right? But it satisfies this very nice equation. Actually, this equation looks much simpler than the solution. Right? So the differential equation is sigma dot is sigma times 1 minus sigma. Right? Now, but we want to use actually the hybrid systems technology, which look at systems that evolve over time and can compute the set of reachable states. So there is one more step. So let me introduce a proxy function where there is an additional dimension t. So g of t comma x is 1 over 1 plus e to the power minus dx. And if I set t equal to 1, then it's basically sigma of x. And then this function g satisfies the equation g dot is xg 1 minus g, right? And it turns out now with this, now it's I can model now a single neuron as actually a one-dimensional dynamical system, right? And if I want to compute, so what was the original symbolic computation problem? If I gave you a range for x, right? If I told you that the input belongs to some set I, where would the output be? Right? Give me an approximation or some estimation of sigma phi, right? A symbolically compute an approximation of sigma phi, right? So if I so I can actually view it as a dynamical system, where the dynamical system is this given by this G, right? It's a time varying dynamical system, and if I initialize just a few minutes ago I showed you how to compute the Rietzsch set of dynamical systems, and if I say that x is the initial set is that t is equal to 0 and x is in I, and if I say that okay, where will this system be for t equal to 1, basically what I would be getting is sigma phi, right? And that's the basic idea. And so this is so with that with this idea that we can actually now translate the neural network into actually a hybrid automaton H prime, compose the plant model with this hybrid automaton, and then apply an existing verification tool. So maybe the last slide was a bit mysterious. This one may make it a little more intuitive, though I mean the technical details are not super relevant, but just to give you a feel. So here is a neural network, very simple one, where there's only one hidden layer. There are two inputs, x1, and suppose I told you x1 is in the interval 2 to 3, x2 is in the interval 1 to 2, and the top neuron is some function of x1 and x2, and it's already been trained. So the 0.3 and 0.2 and those things that you see there are the weights after training, and the output is again some output is actually the output neurons are not sigmoidal. Output neurons are always linear functions of the last layer. So it's some linear function of the previous layer. And the computational problem is, you know, if I told you that the x1 was in this range, x2 was in this range, compute some s, you know, where would y be? Right? That's our problem. But I don't want. I want a symbolic representation for this one, right? And what our tool would do is it would translate it into this kind of a hybrid automaton, where I have one mode for every layer and one mode for the initial for the initial layer, one mode for the output layer, and one mode for every linear layer, for every hidden layer. The number of state variables would be equal to, essentially equal to the number of neurons per layer. And what you see here are, you know, well, in the previous slide I was telling you about this differential equations, so it's really derived from that, right? But if and it's kind of hard to comprehend in real time, but all I want to emphasize is that if you look at a differential equation like here, this is where basically that the equation that the sigmoidal satisfies is, it shows up somewhere here. So there's a bit of non-linearity here, and when so if I initialize the state at time t equal to 0 and I look at the state of the system at time t equal to 1, so t was that auxiliary additional input that I added, then I would basically get the desired thing, right? Yeah. So I can, so this is something that lots of existing tools can actually take. And this is just like, it looks like a dynamical system with different modes, and I could then say, okay, now so for this dynamical systems, if I give this some initialization conditions here, compute the set of y's. Right? So it's just trying to bootstrap off existing technology. And so this was our first attempt, and then so I'll tell you a little bit about the current tools. So actually, if you look inside what the current tools do, then they use to analyze complex nonlinear differential equations, they use Taylor series approximations of these, and we realized that we could actually be doing that at the sigmoidal level itself. And so again, a little bit of recap. You all have seen Taylor series expansions of functions in your calculus class, but the way they play a role here is that if I gave you some complex function of x, I can approximate it as a sum of polynomials. So, for example, f could be a complex function, and I could say that f of x is something a linear term in x, quadratic, and so on. And then if so typically we use unrolling up to say quadratic or cubic, and then there is some interval term that computes the error, right? And that's like that sums up. It's a bound on the rest of the terms, and this is so to compute the good Taylor model approximations, you need a good interval analysis, and this is it works can be done for nonlinear systems. If the dynamics is linear, then actually there are better. You don't have to use these Taylor model approximations, but in this context, everything is nonlinear, so you have to solve that, right? So instead of in the actual tool, then instead of explicitly constructing this hybrid system corresponding to the neural network, we can directly compute the Taylor model approximation, because and that's computationally more efficient. So so actually, I'm going to skip this because it's I don't think it can be explained well in a few minutes. So what's the summary of the analysis results? So yeah. Oh, so that no, that's why we started with sigmoids. Right. So so very good question. So for ReLUs, actually, there is this swish function which kind of gives you a continuous approximation of the ReLUs, and so what we do is replace the ReLU by swish. So actually, there is now more recent work on training neural networks where the neurons themselves are swish functions. But let's suppose you gave me something that's trained using ReLUs, then I'm going to approximate using swish and add the error of that approximation to the error that we will get, for analyzing the swish functions. Yeah. Right, but right, but that does not scale. Right. Yeah. No, but of course, right. So in fact, the first attempts to analyze these were using mixed integer linear programming, where you directly model the ReLUs, but those did not scale. Because I think there are lots, every neuron gives you now this the non-linearity. So you have too many pieces, basically. So this is, but that's not to say that those approaches cannot be made to work, right? So this is, but that's the central computational challenge. How do you handle the non-linearity, right? And this is like one approach, but there are groups trying out MILP-based solvers for this. Piecewise, right? Piecewise, but yeah. No. But it's too many. If you have, let's say, 100 neurons, then you have lots of combinations of these pieces, right? Right. Yeah. So that. Right. Yeah. And then if you can. So in some sense that's what we are doing, and since it's a continuous approximation, we can do some interval analysis and compute the error bounds well, right? Yeah, but but you will get, if you are trying to do symbolic simulation directly on this piecewise linear, you pay the exponential price already, because the number of combinations of all these pieces is going to be exponential in the number of neurons. Right, but in the specific case, our problem is to analyze the closed loop system. So I think these two are actually very different problems. One is I'm looking at just the neural network, and I have a specification of the input to output mapping. In many contexts, getting that specification is difficult, and in fact we had this discussion a while ago that if I'm interested in the classification and robustness of that classification, that's a different problem. And in perception, I don't have a clear high level specification. If I'm looking at a closed loop system where the neural network is feeding control inputs to a dynamical system, then I have a clear specification for the closed loop system, but I don't have a clear specification of input-output mapping of the neural network. Now, to analyze the closed loop system, I have to analyze the dynamics of the plant. And any model of any interesting dynamical system is nonlinear. So there we think that this strategy of translating the neural network into kind of framework that this dynamical system models already look like is a potential win. But it's all, this is like this year's work. It could be obsolete by next year. Okay, so we tried a variety of benchmarks. So this mountain car, and actually I have some slides to give you a little bit of feel for the experimental empirical evaluation. This is a very standard benchmark in reinforcement learning. This quadrotor, and this F110 autonomous racing car controller is one actually we are quite proud of, because this is the first verified closed loop system that's actually, it's deployed in the sense that the controller that we verify is the one that we deploy on this car, and it seems to work as well as the handcrafted things. I mean, in these papers we have more detailed empirical evaluation, but just to give you a rough idea of the scalability. So it's about 10 layers and 100 neurons per layer. It's about 1,000 neurons, which is, but from a symbolic simulation perspective, it's pretty impressive. It's because that's we have all. We were just talking about all these non-linearities, and it's basically it's easily exponential in that 1,000, right? So making it work has been a challenge. Of course, it's this is not good enough though if you are looking at the neural networks on that one would potentially use for autonomous driving. But interestingly, for this low-level control, this is despite all the buzz that you may hear, that nobody is using it. So actually, all this work is sponsored by DARPA for their Assured Autonomy program, and it has been a struggle to get actual neural networks that are being used for control applications, right? So again, as I said, for perception and natural language processing, game playing, it's completely different story. We see lots of great success stories, but those are the applications where you don't need the safety critical guarantees, right? I mean, they are the applications are tolerant to some kinds of errors, right? Yeah, people are not screaming if you get some weird result once in a while. Yeah. 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 No, but we have the model of the car. So, yeah. So that's why the so it's a very good question. So this is called in control we would call it sim to real gap. So I have a simulation model and I have a real model. Now how right? So it's in the end what you are verifying is the model, right? And then you deploy it, and then so this video that I showed you, it's like actually the deployed model, and there of course it's running on the real car, right? But actually, you know, your question is very relevant, which is that unless we show we do not have a compelling demonstration where we find some error in the model and convince people that, oh, you know, this result of the verification tool is actually relevant, right? And that's well, this is work in the early stages, so we haven't hit that spot. So that's a problem with all of verification, because what you are verifying is some mathematical abstraction of what's happening, and people, you know, the industry gets super excited when you find some bugs that have been missed in actual testing. So for testing, you could be testing models, but you could also be testing a deployed system, right? So that's the benefit of testing, because you could be testing the real system, but in verification, you cannot be. But there is still value for formal specifications, because you could extract monitors from the specifications and implement them as watchdogs in the real system, and so that, you know, that would monitor. So in the context of safe AI, there is work on shielding. So suppose you know, I don't trust the neural network. So another approach would be I say, okay, here is a set of safe states, and if you see that if you're getting out of it in the actual deployment, then switch to this much safer version where you just go to the side of the road and stop, right? Yeah, that's, one could try to do techniques like that. Okay, so just to give you a feel for some of the you know, some empirical results. So I don't have slides for the F110 car experiments, but this is from in the earlier version of the tool. So here is a standard benchmark for reinforcement learning. So here is this car. It's actually one-dimensional, so that's why things are simpler. And it's you know, you want to accelerate it so that it can actually go up the hill, but you don't have enough power to standing from stationary to go up the hill, so you have to first push it back and then it goes up, right? So this is called a mountain car, and this is like the dynamics. And the so in reinforcement learning, this is viewed as a benchmark where you know, you need to figure out, depending on the initial position, you know, what strategy should you do, right? So so you try various actions, observe rewards, how far up the hill you go, and then learn the neural network. So if you look at the competitions for reinforcement learning, they would say that you run like 100 random trials for the trained thing, and if you succeed over 90%, then, you know, this is a good controller, right? And which may be good enough in this specific case, but if you are deploying the if let's say this was safety critical and you had to go up the hill, then this is not good enough, right? And what then verification people would say that this, you know, for a given range of initial conditions, which for example in this case could be, you know, this anywhere between this. So I'm not even sampling 100 points. For all these initial conditions, for the neural network that you have trained, establish that the car goes up the hill, right? Yeah. And that's where, so that could be the value of formal verification. And the so yeah, so in this specific case, actually the neural network is small. It's 2 hidden layers with 16 neurons per layer. So the inputs are position and velocity. The output is the thrust. And the so the first thing. So in this case, actually, we found a counterexample for like some specific initial condition. The Taylor model approximation that I mentioned briefly, that actually improves the verification times. So here are some plots, again not not super interesting, but the punchline is that, okay, if you with this current technique, so we can vary the layers from 2 to 10, the neurons per layer from 16 to 128, and this here is in seconds, so it's not super expensive for this simple problem, right? Yeah. Okay, but the more interesting, the case study that we have is on this. So that's what I started with. So this is actually the complete model. So it was a 5-dimensional system with the x1, x2 velocity, angular velocity, and the direction. And so as you can see, these differential equations are kind of complicated. Of course, so as we just discussed, the verification results are good only up to this model of the car, and the actual car, this is just an approximation of how the actual car behaves. Yeah. Right. Good question. So I think the first challenge would be, how do you model that? I mean, you have to construct a model of the environment. In this simpler case, the model of the environment was the walls and the model of the LiDAR. That if the car is here and the walls are here, what would the LiDAR readings be? And you can add error to that, right? Now, so imagine now you have other things, then you would have to model that, right? So you would have to add models of these adversarial agents, but some constraints on how they move, but also a model of your perception system. So actually here the LiDAR was easy to model, but if you have a more complex system, like say a camera, right, you would have to create a model of that. That if I am here and if the cars are moving this way, and what would my camera tell me? So that's a complicated problem. Yeah. Right. Yeah. Right. Yeah. Right. Yeah. So that's there are lots of research, interesting research challenges. Right. Yeah. So this so it okay. So yes, but just to recap, so the neural network controller maps these LiDAR measurements to steering direction. It has 2 hidden layers with 64 neurons, and we verify that the car doesn't hit the walls. So here are some more specific things. In fact, there are some simplifications. We are just making sure that this on this turn it's doesn't hit. So you have to divide it into a number of regions. So there are some more technical details on how this model is created. But the good news is that this verified controller is actually deployed on the car, right? Yeah. Oh, okay. So this that line got broken up, but yeah. So this So just to conclude, so I think we are in how to ensure safety when you have neural network based controllers. It's a challenge from the perspective of symbolic computation. Now, whether these techniques would be useful for actually assuring safety of autonomous driving, I think that's I mean at this point I wouldn't predict that. But just going back to the history of formal verification, so if you look at processor design or the design of web servers and operating systems and so on, the formal guarantees that verification tools can afford came much later than people first built these systems. Sometimes even a decade or 2 decades later, to when some bugs became super relevant, and then people invested in making these tools to apply to real systems, and then we could see the benefits. So for example, the Microsoft operating systems crash a lot less today than they would crash in the 90s if you were around then and used those, the Windows 95 or something like that. And some of the techniques there are based on this, the formal verification technology, right? But now with these recent failures of Boeing and so on, I think there is interest in making sure that the in these safety critical situations that we should have higher assurance, and this verification would be just one of the techniques, and there are many other technologies, but this could contribute to making assurance. So this this sentence got broken, but what I wanted to say was the verification tools are never scalable, just like models, right? None of the models are real. They can model reality, but some models are useful. So the same way, it's a computationally hard problem, and you can't. A scalable verification tool doesn't exist, but some of them have been applied to complex systems to find real bugs. So in the context of these closed loop systems with neural networks, I think what I showed you was actually a first demonstration that something that's verified is also deployed, but there is no compelling case that we found some bug which people didn't know, or it's super realistic or anything like that. The one that's actually of interest to me as a scientific challenge is how would you even prove anything about this neural network, right? Because it doesn't have modular structure. If you have a fully connected feed-forward network, there is some work in machine learning about what does outputs of some intermediate layer represent, right? Yeah, but if you were to write a proof about it, right? That's how we write proofs about complex software or hardware or any other system, by trying to break up the proof, by trying to understand the what is this specific component supposed to implement. Well, in the case of neural networks, there is no such modularity. Right? So this website has, so this tool is called Verisig, and there's some information about that. Right? Yeah. Yeah, so this is so this is back to this video. So it's so the punchline here is that this is a verified neural network to some extent, and that's what's actually deployed. So thank you, and we can take some more questions. Yeah. So in this specific thing, so the only components were the controller, the model of the car, and the lidar. Yeah. And so your question is, what if there were other software components? So in principle, one could combine all those things, right? Yeah. But so the software, of course, will have complexity, but in the specific case, the complexity came from this complex nonlinear differential equations that were modeling the motion of the car, and the fact that the neural network itself is this nonlinear kind of function, right? With software, usually the challenge is scale or complex data structures, but that would add additional complexity, and then I mean, without some understanding of modularity, it would be hard to look at the monolithic system and try to prove something about it. I think I think once you start thinking about integrating with software, it's like additional complexity, and one would have need more research to think about that. Yeah. Yeah, no, that's a very good question, and I wish I could give an affirmative answer, but yeah, but no, actually, you know, I guess in this specific context, the neural network seems to be robust, seems to work well. So we didn't find, yeah, but the short answer is we did not find any real bugs. Yeah. Hmm? Right. Oh, yeah. No, so during that process, yeah, the verification tools found lots of problems, but many times there were problems with our model. Right, actually, the LiDAR, modeling LiDAR is not, it's simpler than modeling cameras and perception and so on, but it's still a challenge. Right, yeah. So it was more, yeah, you are right. It was more for debugging model, not the system. Yeah. Right. Excellent question again. So well, for verification you do need a model. So the answer would be no, I know. But so what we are trying is learn a model. Right? You could say that, you know, I want to suppose, you know, yeah, I want to also learn the model, not just the controller, right? And which is not needed, of course, for deployment, but I need the model for doing some kind of analysis. So forget verification. I want to do some analysis. Maybe I want to do simulation or something, right? So what do we do, right? And maybe the environment is complex. So what you can do is you could say that, okay, you know, I want to build a model of this class, and you know and then actually also learn the model. Yeah. Right. So if you but even when you have a model, there could be benefits to use a learning-based controller for deployment, because yes, because the learning-based thing can be evaluated much faster. For example, right? Yeah. So it's but that's an interesting direction. Right. But in many cases, where yeah, I mean, it's true that maybe you don't have a model. Like, you know, we were talking about pedestrians, or you know, what happens if people are walking in and so on. So well, you could try to learn a model of actually how the obstacles are moving, and then try to verify that in the context of that model, you have a better guarantee. Okay.